Welcome, ladies and gentlemen. Let me present myself. My name is Matthijs van Weveren. I'm with the OpenMP ARB and CS group. And I will present a set of OpenMP use cases today. I've chosen the 7 use cases in different fields, from medical, oil and gas to automotive, financial, and physics fields. The first use case I want to discuss is the speeding up of search for a COVID-19 drug. So when looking for a drug to neutralize the SARS-CoV-2 virus, then medical researchers look for molecules that can dock onto the spikes of the virus and stop it. So for this, there's the software AutoDock, which is a molecular docking application used open source by many medical researchers. And the compute intensive part of this application is a Lamarckian genetic algorithm. So a genetic algorithm is based on and inspired by the work of Darwin on genetics, where you have a population which evolves from generation to generation, and from only the fittest individual makes it to the next generation. There's a fitness function that governs how the natural selection is done, and mutation is also introduced into the algorithm, where different individuals are randomly changed. So this genetic algorithm was parallelized with hybrid OpenMP MPI in this case. So OpenMP is then used for intranode parallelism to split up the work over the cores of a shared memory SMP system. And MPI is used for inter-node communications. So AutoDock, parallelized in this way, is used amongst others on MOGON 2, which is the Mind supercomputer system. And for the rest is widely used by medical research around the world for researching for COVID-19 drugs and other drugs against other diseases. Okay, the next use case is the speeding up of seismic analysis with OpenMP. So seismic analysis is used in oilfield exploration. In the image on the right-hand side, we see that a ship has a line of hydrophones, which are underwater microphones, which capture sound coming from the Earth. And the ship also has an air gun behind him, which is a source of shock waves. The shock waves propagate through the Earth, reflect on the Earth layers, and come back to the microphones. Seismic analysis is then used to analyze the signals captured by the hydrophones in order to make an image of the subsurface. In this case, we're looking at the Minimod application, which is a stencil-based application that solves the wave equation. And the wave equation is, of course, the equation that governs the propagation of sound waves. And the computational intensive part in this application is the stencil computation. That is computation where you have the value at the grid point depends on the values at neighboring grid points. And in this computation has been implemented with OpenMP tasks. So a task-based model is where you have the software creates a pool of tasks, and each task is taken up by a thread, which executes on the core. When the thread has finished the task, the first task it took up, it goes to a next task in the task pool. And so all the threads on the system take tasks from the task pool until the pool is finished. This is the way of parallelizing the computation on a set of cores. So this has been done in the Minimap application, and now it is used by Total and the Stony Brook universities on the Supercomputer Summit and Core in the US, and Total uses it in its oil field exploration. The following use case is the computation of the binding energy of the Coronene dimer. This comes from chemistry. The Coronene dimer is shown in the image. Dimer means two molecules, and we want to know what is the binding energy of these two molecules. This is done with the software NWChem, which is a widely used open source package for computational chemistry. NWChem computes quantum mechanical computations, which are very compute intensive. So in these computations, things like the energy levels of the atoms and the molecules are computed, and from there the different properties of the molecules are calculated, amongst others the binding energy. And these computations are so intensive that these are very good candidates for the forthcoming quantum computers. But in this case, it has been implemented as OpenMP for SMP and accelerator systems. And the intranode and accelerated offload features of OpenMP 4.5 are used. So intranode, that means adapting the software so it uses the cores of a SMP system efficiently. And accelerator offload means offloading computations on the GPU accelerator, for instance, and getting the results back to the host, which is then the SMP system. So this NWChem is a widely used open source package, and it's available on many HPC systems, including Shaheen in Saudi Arabia and Core in the US. The following use case is the speeding up of modeling of subsurface and subsurface flow. On the right, you see an image where computation is illustrated of the modeling of the surface flow, but in bound or modeled with the land surface and atmosphere. And in the case of the European 2003 heat wave. This has been done with these software ParFlow, which is a watershed model to simulate surface and subsurface fluid flow. So watersheds that includes rivers and valleys, and subsurface also caves. And these software uses nonlinear and multi-grid solvers, which are quite computationally intensive, and also couples land and water models, as in the example on the right-hand side, where you have the water and surface are coupled. The ParFlow is implemented as a package with different backends. And OpenMP is one of the backends, so that ParFlow can run on intranode systems. It has been implemented in such a way that it can be eventually used in up to 30,000 processors on supercomputers such as Edison, Cori, Yellowstone, and Juqueen. The next use case is from the automotive field. This is a field where autonomous driving is being researched and developed, where a car has cameras which analyze the surroundings and uses that information to define where it's going. So OpenMP has been used to speed up this process. In this case, in this AutoWare autonomous driving platform software, which is open source autonomous driving software, which is used by several manufacturers. And the mapping module, as you can imagine, is computational intensive. This is the module where the data coming from the cameras is analyzed in order to figure out where the vehicle is actually sitting. This has been implemented with OpenMP device offloading and parallelization directives. You can imagine in the car, you're not going to put an SMP system. So these are embedded systems. And OpenMP is used to offload the computation on the embedded system and get the data back to the host system, and also parallelize on the host, which is a shared memory system. The target platforms, in this case, are NVIDIA GPU and Renesa's R-Car processors. And this is for the device offloading, where you have your computations. Data is then sent to the accelerator. The computations are done on the accelerator, and the results are coming back to the host. So the AutoWare autonomous driving platform is a platform which is available for manufacturers to use. The next use case is the speeding up with OpenMP of European option pricing. This comes from the financial field. European options are options that a buyer buys and can check cash out at a specific time in the future. So he has to wait until that time before using that option. This is a difference from the American option, where the option can be used any time until the maturity date. So this pricing is calculated by solving the Black-Scholes partial differential equations, which have been developed in the 70s already, in order to predict the price of a European option. And this problem is an embarrassingly parallel problem. There are no data dependencies. So it can easily be parallelized with OMP parallel on the shared memory system, on where it has been implemented. And this is a type of work that is done in banks, so and used on their shared memory systems. So let me finish with the physics use case. This is the simulation of process of high energy density physics. On the right-hand side, you have an image where lasers are propagation is simulated. The red is a laser beam below the image, and the green on the top of the image is also a laser beam. So this has been implemented with the Hydra code, which is a multi-physics simulation code with which radiation transfer, atomic physics, and laser propagation is computed. Again, this is a quantum mechanical computation, which are compute intensive. So in this case, we compute the laser photon properties. They go along a specific laser beam. This Hydra has been implemented with the hybrid OpenMP MPI. So this is where you have OpenMP used to parallelize on the node, and MPI is used for the data communications between the nodes. So Hydra has been developed and is used by Lawrence Livermore Lab to simulate fusion and nuclear processes. They have a national ignition facility where they do also the experimental work and coupled with the simulation work. So, well, thank you for your attention. I hope these use cases have been interesting and motivating for you. And good luck with the rest of the conference.